Assalamu alaikum. We have obtained the expression for magnetic field due to a straight infinite long current carrying conductor. In this video, we will obtain the expression for magnetic field due to a current carrying circular coil. For that, I consider this one as a loop or a coil which carries current I flowing in this direction. Now, I said soon is a circular coil. If it is so, what I have drawn is nothing but an ellipse. Why is it so? The reason is I have placed the circular coil in this way, perpendicular to the plane of the board. I cannot show that structure. So to show that it is placed perpendicular to the surface of or the plane of this board, I have drawn it in this way to appear like an ellipse. Then this circular coil have a center at point O. This is the center. I connect the center to the circle, and what do I obtain is nothing but the radius is R. And I do the same thing with this side as well. Draw a dotted line here. Then along the axis, this is the axial line. Along the axis, I take one point. I name this point as P. At point P, which is along the axis of this circular current carrying coil, I will measure the magnetic field. Okay, so to do so, I connect a point P to this point, which is named as C. And this point is taken as D. To make my work easy, I take two line elements at point C and point D. And this one line element, this another line element. Here, both the line elements having a length equal to dl. Here, the length is also same. Again, dl. These two line elements, which are taken on C and D, are kept opposite to each other. They are kept diametrically opposite to each other, as you can see from the diagram. Now, I am going to connect point C to P, and I will do the same thing to point D as well. I connect this to P. This I have done. Now, I will go ahead. Here, I draw a perpendicular line to CP. I name this one as PR. This line is named as PR. This line PR actually represents the magnetic field dB vector produced by this current carrying element. I call this one as the current element now. This is the magnetic field produced by current element present at point C. And from the diagram, it is quite clear that the line PR is perpendicular to the line CP. It is not only perpendicular to CP, but it is also perpendicular to the line this current element IDL, which is shown, which you can see here. Okay, in a similar way, I draw a line here, which is perpendicular to this line PD. I name this line as PS. A line PS is perpendicular to PD, which represents the magnetic field produced due to the flow of current through this line element present at point D. Clear? And here, the magnitude of this magnetic field and that of this one is same, because these two current elements are of the same length. I have shown this to you here. Now, I'll go ahead. Here, I'll write the value of dB vector. For that, I'm going to use Biot-Savart law. Biot-Savart law says that I'll write the magnitude alone. dB is equal to mu naught I upon 4 pi. Mu naught upon 4 pi is equal to, dB equals to mu naught upon 4 pi IDL sin theta divided by R square. So here I don't mention the unit vector because I have taken only the magnitude. Clear? And here theta is the angle between IDL, the current element, and R. What is R here? R is nothing but the length of the line that connects C and P. So, R is a vector. So here, theta is the angle between IDL and R. Clear? And it is found to be 90 degree. Why is it so? Let me tell you. Here, theta is the angle between IDL vector and R vector. Okay. Here we have this vector which connects the C and P. Nothing but that. So here, there is angle between IDL vector and R vector, which is equal to 90 degree. What is the sin of theta will become sin of 90, and a sin of 90 is equal to 1. This is known to us. I box this. So, if I use this one here, what I'll get? I get this. dB becomes equal to mu naught upon 4 pi IDL. Sin of theta becomes 1. So, I don't mention that. So, IDL upon R square. This is taken as equation number 1. Now, let me tell you why theta is taken as a 90 degree. Then I told you it is the angle between IDL and R. Suppose I take the example of this tangent galvanometer, which has got circular coil. Now, here also we have taken one such similar coil through which we pass current. Now, here, this line which connects O and P is we consider this one as I represent that axis which starts from the center of the coil and ends at the point P. Is represented by this scale. Okay. Then, to show this line CP, I take this aluminum pipe, place it here this way. So, what I have shown here is this view. Okay. Now, let's place it something like this. I hope you understand. Now, what is that angle? This angle theta is nothing but this. I place it properly. Now, this angle is theta It is found to be 90 degree. It is obvious. You see this angle. This angle is of 90 degree. And it is represented as a theta in this diagram. But I cannot show that one here. Because if I take this as a theta, it won't appear to be equal to 90 degree. I hope you have understood. So this is how we obtain equation number 1 by substituting the value of theta. Now I'll go ahead. As you can see, these are two lines, PR and PS. Both are tilted by some angle. Clear? Here, magnetic field is a vector quantity. When a vector is inclined at some angle, means it shows variation in both the y-axis, in our case it is z-axis, and as well along this axis. Or in simple words I can say, when a vector is inclined by some angle, it means it shows variation along the vertical and as well horizontal. In both the direction it shows variation. Okay, this is what it means. Okay, so this is the magnetic field produced by this current carrying coil. This shows variation along this axis, and it also shows variation along this axis. So from this, it is quite clear that it has got two components, one along the vertical direction and one along the horizontal direction. Okay. Now I am going to resolve dB into horizontal and vertical components. Okay. So that I take this here, this part, that is here, is B. I consider this one as the vertical component, this one as the horizontal component. To do so, I drop a perpendicular from the tip such that it can intersect here, and I do the same thing to this line as well. I drop a perpendicular so it can intersect here. Now I take this angle to be equal to 5. This angle is taken as 5, and this line actually represents dB vector. When I have drawn this, I have obtained a rectangle which is divided into right angled triangles. Okay, and here I take this right angle triangle. You will do so, this side of this triangle is called the opposite side, and this is the adjacent side, and this one, this pink line represents hypotenuse. Okay, whose value is dB. I take sine of theta to get the vertical component. Sine of theta is opposite side divided by hypotenuse. We don't know the value of opposite side. This is what I am going to find out. Okay, so I keep it as such, and hypotenuse is dB. I take only the magnitude. So I cross multiply to get the value. So opposite side will be equal to dB sine theta. I box this. Where do we have opposite side? This is the opposite side. If its value is dB sine theta, this line which is kept parallel will also give the same value. So what? dB sine theta. I hope I have understood. This is a dB sine theta. If it is dB sine theta, then this parallel line which goes along with it will also have the same value, that is dB sine theta. So we have obtained vertical component of dB vector, which acts here in this way. So I take it this manner, dB sin theta. Yeah, I'll change the color. Then I'll find out the horizontal component. For that, I take cos of theta. Nothing but adjacent side divided by hypotenuse. You don't know the value of adjacent side, so I keep it as such. Whereas hypotenuse is a dB. Then I cross multiply to get the value of adjacent side. Here, adjacent side will be equal to dB cos theta. I have cross multiplied this. Then I box this equation, this value. Now, this is the value of adjacent side. Then we have that. So, this is nothing but dB dB cos theta. Yeah, this dB cos theta. I written here. I'll do the same thing here as well. So here we have this line dB cos theta. This is the horizontal component of a dB vector. Clear? Now I follow the same method to PS as well. So whose value is equal to dB vector. Now I show you here. I take this. dB change the color. So you should not get confused. dB vector. Now I draw two axes. Okay. Now after that I follow the same method. I drop a perpendicular. It forms a rectangle. Okay. And this angle is taken as 5. So then this is our opposite side. This is hypotenuse whose value is dB. This is the adjacent side. Okay. I start with the same method. Here, sin of theta is going to be equal to opposite side divided by hypotenuse. The opposite side is unknown, so I kept as such. Hypotenuse is dB. So, opposite side is equal to dB sin theta. I box this, then I go ahead. Now I take a cos of theta. So, the what adjacent side divided by hypotenuse. Don't know the value of adjacent side. Is kept as such. But hypotenuse is equal to dB. Click on cross multiplication. I skip one step here. So, adjacent side is equal to dB cos theta. I mentioned the value of adjacent side here is a dB cos theta, and it is present over here. Here. Change the color. Equal to dB cos theta, and the opposite side is present here. It is the opposite side. This line goes parallel to it. What is dB sin theta? Then this will also be dB sin theta. So I mentioned that one here. This dB sin theta. Yeah. Now, if you look at this diagram carefully, you find that dB cos theta and dB cos theta, they act in the same line but opposite to each other. So they cancel each other. They just cancel each other. Okay. Whereas dB sin theta and dB sin theta of this part both act along the same direction, and also they are in the same line. Okay. So this component of dB vector alone contribute in the magnetic field. Got it? So I can say that from here dB vector is equal to dB sine of a angle. Oh, here I have done a mistake. The angle is taken as 5. If it is so, then everywhere I should take this to be equal to 5 only. Okay, not theta. It is 5. Actually, everywhere. It is 5. 5. Why 5? Because the angle taken by me is 5 here. 5. Also 5. And I will make the same changes here as well. So 5 is 5. This is also 5. This one also represents 5. If it is so, then dB vector can be taken as dB sine of angle 5. Got it? So let me mention that angle here in this diagram. So I have mentioned them here. This 5 and this also 5. Got it? It is so. According to geometrical rules, this angle will also be equal to 5. So I proceed. Got the value of dB vector, which is equal to dB sine 5. Now, to get the B vector from a dB vector, I need to integrate this. If I integrate, I will get a B vector. Before I proceed, let me give the direction to this part of the equation. Here we have dB vector. This side, to provide the direction, I use unit vector. What is that unit vector? Here, dB sine 5 acts along this line. So, I take K cap. Where is it shown? Let me show this to you. For that I draw a coordinate system. So this stands for X, this stands for Y, this stands for Z axis. Okay, and dB sine 5 is along the Z axis. We know unit vector along X axis is I cap, and along Y cap is along Y axis is J cap, and along the Z axis is K cap. That is why I have taken K cap here. Here dB sine 5 acts along the Z axis, and the unit vector along the Z axis is nothing but K cap. Now, after multiplying this with the unit vector, I get the direction. Now, next, if I integrate this, I will get the total magnetic field due to the flow of current in this current carrying loop in this coil. Now, what about this dB vector? The dB vector gives the magnetic field at point P due to the flow of current in this line element alone. Okay. And why do we get the B vector from integral of dB vector? Let me show this to you. Here we know that if you integrate dx, we get dx. In a similar way, if you integrate dB vector, we will get B vector. This is what I have shown here. Now I am going to substitute the value of dB vector from here. By doing so, what do I get? I get this. dB sin phi k cap. And I know the value of dB is mentioned here in equation number 1. So from here I'll get B vector to be equal to integral of this mu naught upon 4 pi IDL 1 r square. This is the value of dB. Then what remains here? Sin phi k cap. Now if you look at this equation carefully, you will find that this portion is a constant. So we do not integrate constant, so it is taken outside. I'm sorry, not this question. This portion is a constant. Okay, so we integrate only this part. Remaining terms are taken outside. Let me show this to you here. Take the mu naught I divided by 4 pi r square sin phi taken out along with the k cap. Then integral symbol with a dl. Here dl is the length of this line element. Clear? I'm going to integrate this alone. So for that, what I'll do, I take the limit as 0, lower limit as 0, and upper limit is taken as 2 pi r. The 2 pi r is the circumference of this circular coil. If I integrate this from 0 to 2 pi r, I'll get the entire length. It covers the entire length of or entire circumference of this circle. Got it? And it will provide me the total magnetic field. I'll go ahead now. Now write this part as it 4 pi r square. So I'll find out what is the sin 5. Now that I'll substitute here. Before that, let me integrate this. Now if I integrate dl, I'll get dl. We're following the same formula. The limits are written outside. 0 here, this 2 pi r. Okay, then expand this. mu naught I 1 4 pi r square sin 5 k cap, and here I substitute the upper limit. In the place of here is 2 pi r, then minus lower limit. In the place of here I write the lower limit is 0. This is what I get. Right? Now I don't know what is the value of sin 5 that I mentioned. Okay, to do so, I take this triangle, right angle triangle, OPC. This O, this C, this is, I'm sorry, this C, this P. OPC. Here the distance between OC is taken as capital R from the diagram, and the distance between CP is taken as small r from the diagram. Okay, so what is OP? Here OP is nothing but Z. Okay, but I have forgot to mention. Here point P is at the distance of Z from O. Why Z? Because this line is taken along Z axis. So the length is taken as Z. Clear? This is a right angle triangle. I apply Pythagoras theorem to this. Apply Pythagoras theorem. Pythagoras theorem. What is it if you do so? It says that r square is equal to sum of square of remaining sides of the triangle. This r square plus z square. This is the value of r square. From this, r is found to be equal to root of r square plus z square. This root can be mentioned this way, r square plus z square. Root of this value can be mentioned, can be represented r square plus z square power half. Clear? This is the value of r. Then I will find out the value of sine of phi. Here the angle between OP and CP is nothing but phi from the diagram. This phi. What is so? This is the opposite side. This axis hypotenuse. This one is the adjacent side. Like at sine phi value. For that, sine of phi is nothing but opposite side divided by hypotenuse. Here the opposite side is r and the hypotenuse is small r. Clear? So from this, we obtain the value of sine phi. So sine phi is equal to, we know the value of r that I am going to substitute here. This part equal to r square plus z square power half. Okay, so we have the value of r and sine of phi. This I am going to substitute in this equation to get the magnetic field. Substituting r and sine phi values. Where here. Here if I substitute, I get what I get. I should just do, I get b vector is to be equal to mu naught I upon 4 pi. What is r square? No, here one more thing I mentioned, including r square, r and sine phi values. I start with this. R square value is what? R square plus z square. Then sine phi value is sine phi is nothing but r divided by r square plus z square power half. Then what else is left? K cap. Then is multiplied by 2 pi r. Clear? Now this pi and this pi will cancel. No. This 2 and this will cancel. The next step, what do I obtain is with this? B vector is found to be equal to mu naught I upon 2. Then I multiply this part with this. If I do so, what I will get? I will get this. But before that, in numerator, I have r. Here also I have r. So r and r get multiplied and provide me r square. If I multiply these two, here the power is, we have no power. That means power is equal to 1. Okay. When I multiply these two with which have different powers, then in such case we add the power. What do I get is r square plus z square. See, when I add 1 with half, what I will get? I will get a 3 by 2. Okay. So power 3 by 2 here. K cap. Here, if Z is taken equals to 0, why 0? Now, if I keep reducing, if I bring P towards O, the value of Z will decrease. When P is kept on O, the value of Z becomes 0. So, in such case, if Z equals to 0, then what happens? B vector becomes equal to mu naught I upon 2 R square divided by, this has become 0. So what remains is R square power 3 by 2. Okay. Write this one here. Close the bracket. This is the final equation which provides me the magnetic field due to the current carrying coil at a point of P. Okay. Note I upon 2. Here, see what happened. R square. Here, square and this half will cancel. And what remains is something but R cube. K cap. Right? Now, again, see this and this get cancelled. And what remains here at the end is nothing but this. P vector is equal to P naught I upon 2R K cap. This is the final expression which provides us the magnetic field at point P due to this current carrying coil. Suppose if this coil has got n number of turns, then that can be represented as this way. Magnetic field in that case, if it consists of n number of turns, then I mentioned n here, which represents the number of turns in the coil. 2R. K cap. This is the final expression of magnetic field due to a current carrying circular coil. I hope that video is useful. If you have any kind of doubt related to the topic, can you put your questions in the comment section. Thanks for watching.